Hi, folks. I'm going to be talking about our paper, Tree Embeddings for Hop-Constrained Network Design. I'm Ellis, and this is a collaboration with my advisor, Bernard, and Goran, who is a postdoc at ETH Zurich. So network design is this great field, in theory, that's all about trying to find networks that satisfy certain connectivity requirements. And in particular, what we'd like is that our networks are cheap, fast, and reliable. So the sorts of connectivity requirements that people care about in practice are quite varied. So you might imagine that you're given some collection of computers and you want to build out some network so that all of your computers can communicate with one another. Or alternatively, in the perhaps frightening world where cars are composed of tires and steering wheels, maybe you want to build out a transportation network, which guarantees that each of your car factories has access to some steering wheel factory and some tire factory. So given the sort of varied connectivity requirements that people are interested in practice, theory has produced a whole variety of connectivity problems. In particular, the way these problems are usually formalized is you're given some weighted graph, and your goal is to find some minimum weight subgraph that meets some kind of connectivity requirements. Now, what these connectivity requirements are determine different kinds of problems, but in general, these problems kind of fall into a hierarchy of generality and difficulty. Where at the bottom of this hierarchy, you have less general but easy problems like minimum spanning tree, and at the harder and more general end of this hierarchy, you have more complicated problems with very general connectivity requirements. A little bit more specifically, we all know and love the fact that minimum spanning tree can be solved in polynomial time, but all these other problems are NP hard. And in particular, the ones sort of in the middle of the hierarchy admit constant approximations, but the ones at the bottom only admit polylogarithmic approximations. All right, so what exactly these problems are won't be super important for my talk, but I'm going to use Steiner forest as my running example. So let me be very clear about what Steiner forest is. So in Steiner forest, again, you're given some weighted graph and you're looking for some minimum weight subgraph. And here you want to find a minimum weight subgraph that connects a bunch of specified SITA pairs. So you might imagine you're given one pair S1 and T1 and another pair S2 and T2, and you want to find a subgraph so that S1 is connected to T1 and S2 is connected to T2. So for example, this blue solution is a feasible solution for this Steiner forest instance, as is this other blue solution. All right, so returning to our picture of network design, it's clear that these cheapness constraints are sort of captured by the fact that we want to find minimum weight subgraphs. In particular, we can kind of just imagine that the weights are costs, and then that's exactly what a minimum weight subgraph is modeling. But it's less clear how a lot of these classic network design problems model the fact that we want fast and reliable networks. And in fact, a lot of these classic network design problems don't really distinguish between solutions which are and are not fast and reliable. So consider the case of minimum spanning tree. When you solve minimum spanning tree, there might be many different minimum spanning trees. So one of your MSTs might just be a path. Another one of your MSTs might be a star. But I would argue that in terms of speed and reliability, the star is preferable to the path. Why is that? Well, imagine that you're trying to send a message from some node U to some node V. Now, if each edge incurs some latency, then in the path graph, in sending a message from all the way on the left to all the way on the right, you may end up with like a linear in the number of nodes latency. Whereas in the star graph, you only ever have to traverse two edges, and your latency is always going to be some constant. As far as reliability is concerned, if you imagine that messages are dropped from each edge with constant probability, then in the path graph, you'll have a vanishingly small, and in fact, exponentially small probability of successfully sending a message from U to V. But in the star graph, again, you'll always have some constant probability of succeeding just because your message only ever has to go over two edges. All right, so that in these ways, the star MST is kind of preferable to the path MST. But abstracting out what makes the star preferable to the path, it's kind of the fact that it's hop constrained in the sense that not only does it satisfy its connectivity requirements, but it does so with connections that don't consist of too many edges. So in the ways I've described, hop constraints can enable networks which are both fast and reliable. And I'm not just kind of saying this for the purposes of this talk. Here's a citation dump of some of the many papers in OR and even of people who are genuinely in systems and empirically study these Hopkins-Ray networks and observe that they perform better than their non-Hopkins-Ray counterparts. So returning to our picture of network design, this whole speed and reliability business can be modeled by hop constraints in the way that I talked about. So at this point, you might say, like, great, like, I always want my network to be hop constrained. Let me just go to all of my favorite connectivity problems and stick the word hop constrained in front of all of them. In particular, you can imagine the situation is as before, but we're also given some hop constraint, and we want to guarantee that we satisfy each of our connectivity requirements using paths that consist of at most some h many edges or hops. So for the case of Steiner force, what does this mean? Well, imagine for a second that your hop constraint is 2. Then what you want to find is a subgraph that connects corresponding pairs, but using paths consisting of at most 2 edges. So for example, this previous solution would not be feasible because, for example, S1 can now only reach T1 using a path of 5 edges in this blue solution. But the other solution we saw earlier is feasible because each corresponding pair has a path to between the 2 vertices that consists of at most 2 edges. Okay, so this brings me to like a high level overview of what our results are. So if you take nothing else away from this talk, I think this is the slide to remember. So basically what we show is that if you want to solve a hop constraint network design problem, you can just assume that your input graph is a tree. Now, why is this useful? Well, problems on trees are typically much easier than they are in general graphs. So this can kind of form the foundation of many new algorithms for hop constraint network design. Let me describe this in a bit more detail. So the first thing we show is a so-called metric embedding result. In particular, we show that the relevant notion of distance when you're performing hop constraint network design can be well approximated by a distribution over trees. What's this notion of distance? Well, these are the hop constraint distances, which are like the shortest path metric, but where you restrict yourselves to paths not consisting of too many edges. So the general picture is like you have some graph, and then you're going to produce some distribution over trees where distances in the trees are a good proxy for these hop constraint distances in the graph. And these won't be trees on all of the vertices, but they'll be trees on something like 99% of the vertices, most of the vertices. Okay, now using this embedding, we're able to give the first polylog bicriteria approximation algorithms for the hop constraint version of a lot of classic network design problems. And the way we do that is we provide a new sort of general template for solving hop constraint network design. How does this template work? Well, you start with your hop constraint problem. You apply this embedding fact, and that gives you a non-hop constraint problem on a tree. Now, a non-hop constraint problem on a tree is much easier than a hop constraint problem on a graph. So you can run your favorite algorithm to solve the tree problem. That'll give you some solution, and then you just project that solution back into the original graph. And because of this whole partial business where trees are on most of the vertices, you might have to repeat this log n times to satisfy all your connectivity requirements with high probability. Okay, so that's our result at a high level. And now for the rest of the talk, I want to just try and convince you that what we're doing is really just on the edge in terms of what is possible as far as hop constraint network design. And in particular, I'm going to provide 2 things which make hop constraint network design really difficult and which seem to almost make what we're doing impossible. And after I've provided that context, I'll return to our main results, describe them in more detail, and tell you sort of what are the crucial points in our results that allow us to overcome these 2 difficulties. And I'll just quickly end with some directions for future work. All right, so the first difficulty. Returning to our picture of all of our favorite hop constraint network design problems, you might say, like, great, these problems sound motivated. I'm going to go like search around on the internet for what's known about them. And if you did that, you'll find that at least prior to this work, there's nothing known that's non-trivial for many of these problems. And I think this is in part due to the fact that adding hop constraints to problems makes them really hard. So again, minimum spanning tree is NP, but as soon as you add these hop constraints to minimum spanning tree, it becomes NP hard. Now, the situation is even worse than that. there's actually a known logarithmic hardness of approximation for hop-constrained minimum spanning tree. So it went from NP to omega log n hard to approximate. And as you move further down in the hierarchy, the situation starts to look even worse. For example, this hop-constrained Steiner forest problem is known to be so-called label cover hard. So this is this funny like 2 to the log to the 1 minus epsilon n hardness of approximation for any epsilon greater than 0. But if you imagine epsilons tending to 0, this is basically a polynomial hardness of approximation, which rules out all but the most trivial of algorithms a lot of the time. So that's really the first major difficulty is we provably know that adding hop constraints makes a lot of problems hard. And specifically under standard complexity assumptions, we don't expect there to be polylogarithmic approximation algorithms for these problems which run in polynomial time. So already it seems like providing good algorithms for these problems would require solving some big outstanding question in complexity. Okay, so that's our first big difficulty. Now, for the second difficulty, to describe the second difficulty, I'm going to have to first describe to you why a lot of the time network design is tractable, not that hard. Okay, so when you're doing network design, the natural notion of distance to consider is just the so-called shortest path metric. So here, the distance between two vertices is just the minimum weight of a path that connects them. Now, why is this a natural and or useful notion of distance? Well, the good news for network design is the shortest path metric is genuinely a metric. Now, what's so great about metrics? Well, metrics have a lot of structure that we can pull out of them and exploit. In particular, a lot of the time when you're solving a network design problem, you can sort of start with these shortest path distances, apply your favorite theorems for metric embeddings. Those theorems in turn will give you some kind of structure on your problem. And then you can exploit that structure to come up with algorithms for your problem. For this talk, the relevant notion of a metric embedding will be a so-called tree embedding or probabilistic tree embedding. And the structure that this gives you on a problem is it lets you sort of pretend that your graph is a tree. So instead of solving a problem on a general graph, you're solving it on a tree. Okay, so turning now to hop-constrained network design. Here, and we'll kind of see later why this is the case, but here, the natural notion of distance to consider are the so-called hop-bounded distances. In particular, the h hop-bounded distance between a pair of vertices is just defined as the minimum weight of a path that consists of at most h edges and connects those vertices. So whereas before the distance between these two vertices was 4, the 2 hop-bounded distance, for example, would be 6, because there's only this one path that consists of only 2 edges that connect U and V, and it has weight 6. Okay. So you might say well, if that's the natural notion of distance to consider, let me just go to that picture and then replace everything that has an instance of the shortest path metric with these hop-bounded distances. Okay? So if you want to do something like this, the very important word to consider here is metric. In particular, we want to apply facts from metric embeddings to this notion of distance that's natural to study when doing hop-constrained network design. But if we're doing that, it better be the case that the distances that we're considering are actually metric. And in fact, it's very easy to see that this is not the case. So consider, for example, a path graph as follows, where every edge has weight 1. Then the 2 hop-bounded distance between vertices U and V will be 2, because there's a path that consists of 2 edges and has weight 2. Symmetrically, the 2 hop-bounded distance between V and W will be 2. But the 2 hop distance between U and W is infinity. So all of this is just to say that for these hop-bounded distances, the triangle inequality doesn't hold. And metrics without triangle inequality don't really have all that much structure that's useful, at least for the purposes of these kinds of algorithms. So at this point, you might say, well, okay, it's not exactly a metric, but maybe it's close to a metric. And we're only trying to maybe approximate this notion of distance with a metric anyway. But it's actually not too hard to see that there's no metric which simultaneously approximates all of the hop-bounded distances on a graph at once well. In particular, you'll always incur some trivially large approximation factor, which is something like the aspect ratio, which you can think of as like polynomial n if you like. All right, so that's the second difficulty, is this really nice fact that weights induce symmetric in network design is just not true when you're doing hop constraint distances and thinking, or hop constraint network design and thinking about hop constraint distances. And in particular, what's really bad is because these hop constraint distances are really far from being a metric, you can't hope to come up with probabilistic tree embeddings for them in the classical sense, at least. All right, so just summarizing our two difficulties. First, we saw that hop constraints make network design problems much harder, and we don't expect there to be polylogarithmic approximations. And then we saw that there's no such thing as a metric that approximates all hop constraint distances well. So the title of this talk is Tree Embeddings for Hop Constraint Network Design. So something has to give. As far as this first difficulty is concerned, the crucial thing to note here is that these hardness of approximation results only hold for unit criteria approximation algorithms. In particular, if you allow for an approximation factor both in the hops and in the weight, then these hardness of approximation results no longer hold. And using this kind of bicriterionness will be sort of crucial to our algorithms. Now, for the second point, I've been sort of belaboring the fact that no metric exists which approximates hop constraint distances on all of the vertices. So it's possible, and in fact, what we show is there are metrics that approximate the hop constraint distances on most of the vertices. And we'll see momentarily what that means formally. All right, so one more time, what are our results at a high level? Well, we give these metric embeddings for hop constraint distances, and then we use that as the foundation to come up with new approximation algorithms for hop constraint network design. Okay, so let me describe the metric embedding result in more detail. So here, we're given some weighted graph and some hop constraint, and we're going to show how in polynomial time you can sample a tree from a distribution where all of these trees have depth log n, and you have approximation factors alpha and beta, both polylogarithmic, in our case, log squared. So the general picture is like you have some graph, and you have some distribution over trees that you're able to sample from. And these won't be trees on all of the vertices of the graph, but any one vertex will have a very good probability of showing up in this tree. So imagine that like any one vertex shows up in the tree with probability 99%. And this is just some arbitrary constant. You can make it as large as you like. Okay. Now we'd like for our tree the distances in our tree to be a good approximation for the hop constraint distances in our graph. So that's what the next point is. It says that if you look at any two vertices which you successfully embed into the tree, then the regular shortest path distance on those two vertices is going to be at most alpha, which is like log squared, times larger than the hop constraint distances in the original graph. All right. Now the second point is trivial to achieve if you just set all of the weights of the edges in the tree to be 0. So you want some kind of converse, some so-called non-contracting property to balance this out. And that's what the third point is. So this will say not only are the distances in the tree not much larger than the hop constraint distances in the graph, but they're also at least as large. Now, the notion of at least at large is a little bit nuanced here. In particular, the distances in the tree will only be larger than not the h hop bounded distances, but larger than the beta h hop bounded distances. So notice that by looking at beta h hop bounded distances, again, where beta is like log squared, you're only decreasing your notion of distance because you're sort of looking over paths consisting of beta h edges, or at most beta h edges instead of at most h edges. All right, now if you want, the second point is kind of a deterministic fact. It says if two vertices are successfully embedded, then definitely their distances won't be increased by too much. But if you want something more in expectation, you can get a better alpha factor, and we do that in the paper. Now, just to point out where we overcome these difficulties, this beta factor is going to sort of naturally propagate through to our algorithms as a bicriteria factor in our approximation. So that's one place where we're very explicitly using the bicriterianness of our algorithms. And this first point, just summarizes the fact that these are partial tree embeddings. They're embeddings that work on most of the vertices. And if you're familiar with Ramsey embeddings, this is basically the same thing. Okay, so what does this allow us to do? Why is this embedding fact so great? Well, it lets us realize the following general template. So here, we start with some hop-constrained network design problem on some weighted graph, think like Steiner forest. Then we just sample one of these embeddings where the tree we sample is supposed to be a good approximation for the hop bounded distances. Then we solve the induced problem on the tree that we sample. And in particular, we solve the non-hop constrained problem on our tree for all of the connectivity requirements that are sort of successfully embedded into the tree. So in the case of Steiner forest, you can imagine that for each pair that has both of the constituent vertices embedded into the tree, we'll connect them in the tree. Now, after doing this, we just project our solution back into the graph to solve our problem. What do I mean by project back into the graph? Well, if you think about an edge in the solution on the tree, by this non-contracting property that I laid out in the previous slide, this edge corresponds to a path of only less weight that consists of at most beta h many hops, okay? So if you do this for all of your edges, you'll find the very nice property that if a pair of vertices was connected in the tree, then it will be connected in the graph, but not just connected in the graph, but connected in the graph by a path that consists of O tilde h many edges. Okay. Lastly, we might have to repeat this log n times because it's a partial embedding on most of the vertices. We need to satisfy all of our connectivity requirements. Now, if you're familiar with probabilistic tree embeddings, it's tempting at this point to conclude the following. If it would seem maybe that like if I now have a row approximation for these problems on trees, in particular for the non-hop constrained problems on trees, then I can give you up to some polylog fudge factors row approximation for the hop constrained problem on general graphs. But this is actually, you can't immediately conclude this at this point. And I don't really have time to get too much into the details, but there's something sort of subtle going on here where when you're using these probabilistic tree embeddings, it's not enough just to show that you can project from the tree to the graph, but in order to show that there's a good solution in the tree, you have to show how to project from the graph to the tree. And this is trivial in the non-hop constrained world, but when you move to the hop constrained world and these partial embeddings, it becomes more complicated. And intuitively, the rough issue is that the way that some of the edges of a subgraph in your original graph might project into the tree might require using some vertices that were not successfully embedded. So it's not so clear like how you should project from the graph to the tree in a principled way. All right, so in the paper, we figured this out, and basically up to some constants, you don't have to worry about this stuff. And I'll point out this fact about projecting from the graph to the tree is really just for the sake of analysis. It doesn't show up in the algorithms. Okay, so using this template, we give the first polylog bicriteria approximation algorithms for a lot of problems. These include offline problems, their online generalizations, and their oblivious generalizations, which is like online but harder. Now, the details of these algorithms aren't so important, but I think the cool thing to note here is that we know that for even just like offline hop-constrained Steiner forest, we shouldn't get a polylog approximation. But by using bicriterianness, we're able to beat the known hardness of approximation, this label cover hardness of approximation for Steiner forest. All right, so let me just conclude by pointing towards some future work. So I think really the biggest question about here, or about this work is how can we improve the upper bounds and how can we prove non-trivial lower bounds? We don't know any lower bounds that don't just sort of immediately follow from known lower bounds on regular probabilistic tree embeddings. And I hope that I've convinced you that not only are these hop-constrained problems practically motivated, but they're very theoretically rich. Like you can kind of just stick the word hop-constrained in front of your favorite combinatorial optimization problem. There's probably something interesting there to study. Lastly, let me just plug 2 follow-up work. So this paper is really the first in kind of a trio of papers. So if this was interesting to you, you should check out these other papers, which will both be held on Thursday of STOC. So thanks, and I hope to see some of you at the poster session.